Welcome to the distinguished lecture series of the Indian Mathematics Consortium. The aim here is to host virtual colloquia by some of the best researchers and expositors around the world. The speakers are carefully chosen by the scientific committee from among mathematicians who are not only distinguished researchers, but are also known for the quality of their exposition. The principal aim here is to make the talks as widely accessible as possible, especially to PhD students. With this in view, the format of most of the talks will be in two stages. First, there will be a pre-recorded talk by the speaker, which will be posted online. Interested audience can then view this at their leisure and communicate questions, if any, to the organizers. The second stage will be a live interactive session between the speaker and interested participants, and that will be held about 2 weeks after posting the online talk. The approximate duration of the talk will be about 45 minutes, and that of the interactive session will be about half an hour. The distinguished lecture series is co-hosted by IIT Bombay and ICTS Bangalore. Welcome.
It's my pleasure and honor to introduce Laura DeMarco, Professor of Mathematics at Harvard University and one of the leaders of complex dynamics, as well as the emerging field of arithmetic dynamics. In her early work, DeMarco introduced the bifurcation current to study the stable locus in moduli spaces of rational maps and constructed a dynamically natural compactification of the moduli spaces with tools from algebraic geometry, potential theory, and geometric topology. Both ideas were groundbreaking, opening new directions of research in complex dynamics. In joint work with M. Baker, she formulated a far-reaching conjecture about arithmetically special points in the moduli spaces of rational maps, analogous to and containing overlaps with the Andre-Ott and related conjectures in arithmetic geometry. They proved cases of the conjecture with methods involving a remarkable confluence of ideas from complex dynamics and disparate fields such as logic, number theory, and analysis on Berkowitz spaces. In a series of papers with Kevin Pilgrim, Laura studied basins of infinity of polynomials in one complex variable. Their work significantly enhanced the understanding of topological and conformal conjugacy classes of polynomial basins of infinity and the structure of the shift locus in polynomial parameter spaces. Among many other results, they proved a far-reaching generalization of connectedness of the Mandelbrot set. The breadth and the novelty of the ideas appearing in her work have been recognized internationally. She was elected a Fellow of the American Mathematical Society in 2013 and a member of the National Academy of Sciences in 2020. In 2017, she received the AMS Ruth Lytle Satter Prize in Mathematics. She was also an invited speaker at the 2018 International Congress of Mathematicians. Her most recent work on arithmetic dynamics established direct connections between the theory of bifurcations in complex dynamics and the study of rational points on elliptic curves. Her work with Krieger and Hexi uniform Manin-Mumford for a family of genus 2 curves published in the Annals of Mathematics, won the 2020 Alexanderson Award of the American Institute of Mathematics. The present talk is the public lecture delivered by Laura at Santa Clara University on the occasion of the Alexanderson Award ceremony.
Okay, thank you. Thank you for that. Thank you for the introduction. It's really an honor to be able to do this, of course, to receive the award, but to be able to come here and to speak, especially this year. I'm sorry I didn't have a chance to meet Professor Alexanderson. I would have liked to get to know him. Sounds pretty amazing. So, in his memory, then, I will give this lecture, and my goal is to tell you some things about my own work, to describe some of the mathematical ideas that went into that particular paper, but also more generally where those ideas were coming from and what they're related to. So the title of my talk is Complex Dynamics and Arithmetic Geometry, which really means that, wrong button, no, this one, there we go. I'd like to describe a particular connection between two areas of mathematics that are not usually connected to one another. On one hand, an area called Dynamical Systems, which refers to the study of objects that are evolving in time, things that depend on time, and number theory, which I think many of you are more familiar with, our study of numbers, number systems, and solutions to equations. And so with this talk, I'll give a couple examples that illustrate how these two areas might be connected, but especially how the two areas came together and helped us do the work that we did for this particular paper that I'm hoping to explain something about. All right. Okay, so the next slide is a little bit more for the mathematicians in the room. I realize not all of you are mathematicians, but this slide is intended as a sort of outline of what I plan to talk about with a little bit more mathematical language. So let me just go through this overview of what I plan to say. So the basic idea of what I want to describe is to discuss some class of dynamical systems, which I said are objects that are modeling something which is evolving in time. And those dynamical systems take place on a geometric space, which looks like a sphere. And one of the key inputs to that study is from number theory, from the area of arithmetic geometry. So I will spend most of my time this evening talking about how we've used tools from number theory or arithmetic geometry to understand some of these systems. And then the article that I want to tell you about was more about how we then went in the other direction, going from some information about dynamical systems through a study of geometry and arithmetic of surfaces that look more like this one, continuing to surfaces that look more like this one, namely curves of genus at least 2, in this case curves of genus 2. But ultimately, what I'd like to describe, if I have time, is how this brings us back to the number theoretic side of arithmetic geometry. So I'd like to describe this cycle of ideas that are all related to this work. All right. Oops. Okay. So the dynamical systems in question are of a very simple type. The time evolution is really just considering a particular recursive equation. In this case, a recursion which is defined by a very simple polynomial. So we're looking at the iteration of a polynomial. Here you should think of C as just some fixed complex number. Could be 0, could be 5. Think of it as fixed. Could be I. And the dynamics comes from starting with a complex number. This is the notation for the collection of all complex numbers. So starting with a complex number, say I call it Z0, applying the polynomial to get a new complex number, and then inputting that into the polynomial and repeating. So the recursion is just defined by a simple quadratic polynomial equation. Start, say, with 0, I'll put C, then get C squared plus C, etc. So this is dynamical in the sense that we're repeatedly applying this recursive equation forever. That's the time passing. This particular family of examples is very, very famous and very, very well studied in dynamical systems. This is the family which generates the well-known Mandelbrot set, which you may have seen before, perhaps don't know its definition. I just wanted to include the picture, so you see I'm not going to say anything about the Mandelbrot set today, except at least to give you its definition, in case you haven't seen it before. The Mandelbrot set, this is a plot in the complex plane corresponding to the parameter C, where you're thinking of all of these recursive equations, recursions simultaneously. And so just by definition, this is the set of C values for which if you've studied the orbit of 0 under this iterative process, that orbit remains bounded. It does not blow up to infinity. And that's what this beautiful object is. And it has a very important significance for understanding dynamical systems, both in this, for this family of examples, but actually in a much more general setting as well. It plays a very important role, which I will not talk about today. What I do want to talk about is maybe a relatively simple question, that one of the most important things that we want to understand when given any dynamical system is which elements of the space, in this case the set of complex numbers, which elements might be periodic. For what starting points do you return back to yourself? So periodic just means I start with some z0, I repeatedly apply this polynomial recursively, and then I come back to my starting point. So z0 is said to be periodic if it returns to the start. We also have this terminology, z0 is said to be pre-periodic if maybe after some number of steps it doesn't return all the way back to the start, but it begins to cycle. So this sequence of complex numbers that you get is finite. So these are the information of these periodic points or pre-periodic points, how many there are, where they are, give us basic information about the system. And so it's a number one thing that we might want to look at in order to understand any given dynamical system. In this case, I should just observe, there are in fact infinitely many periodic or pre-periodic points for this particular type of system. It's really just a matter of looking at some simple algebraic equations. So for example, if you fix one of your systems, in other words, I fix my complex number C and look at this iteration for that particular polynomial, then the points that are periodic are just solutions to a particular polynomial equation. So this is just some polynomial equation in Z, and all of the roots of the polynomial equation are periodic. So I just wrote down an example so you could see what one of these looks like. When n is 3, so I take 3 steps, then the equation looks like this. When m is 1, I take in 1 step and it looks like this, and I'm setting the two things equal, and I get some polynomial equation of degree 8. It has some roots, and those are the pre-periodic points that satisfy that particular relation. Of course, we could do this for any choice of n and m, and I get a whole list of polynomials, and they all have roots, and so I get an infinite collection of points. And so, let's have next. All right. And so the next question is, what are these sets of periodic points and pre-periodic points for any given example? Now, the following pictures you may have seen before. These are all illustrations of what's called a filled Julia set associated to these polynomials. Those collections of periodic points have some very interesting geometry. For each fixed value of C, if you were to just plot all the points which are periodic, you won't see this picture. This is a filled-in picture. But in this particular case, you would see a dot at the center, and then you would see the circle. The points would be dense in the boundary of this black region. And in each of these cases, it's the same idea. You get perhaps some discrete collection of points on the inside, but then they would be clustering on the boundary of these sets. The periodic points are dense in the boundary of these sets. The filled Julia sets, by the way, are just being plotted as for each fixed value of C. If you start running this iteration and you just check, when does it get big? If it doesn't get big, then you color black. If it does get big, then you color the pixel. It's a very simple algorithm to plot these pictures, and as it has been studied for many years, you get these remarkable and beautiful fractal images from doing this iteration for this very, very simple class of examples, these polynomials of degree 2 for different choices of C. Now, each of the ones I've shown you on this slide correspond to examples where these these filled Julia sets that I'm showing you happen to be connected sets in the plane. But as many of you know, that's not going to be the case for all values, all of these polynomials. Here's a few more examples. If you take c equals I and you plot the periodic points, in fact, the set of them is so thin you can't see it, so you see them traced out in yellow. There's a very thin black set in there. So all of the periodic points are in this lightning bolt region. For this value of c or for this value of c, you see different regions. So here you see actually the set of all of the periodic points and pre-periodic points are clustered inside this yellow region. Their closure forms a Cantor set in the plane. Here are just a few more pictures in case you haven't seen these before. A few more examples of C values. So you get lots of beautiful, interesting shapes by doing this. And so, a basic question then is, so we're interested in these periodic points. To what extent does that collection of points, those sets of periodic or pre-periodic points, determine the dynamical system? To what extent is that collection of points really an invariant? The system is really determining the dynamical system. And by the way, by just a set of points, I really just mean the geometric configuration. I have some collection of points in the plane. I forget the data of how I produce them. I'm just remembering their shape. So you could ask this question. There's a basic fact, or a well-known fact in this particular field, was proved a number of years ago by Baker and Raynaud, that indeed if you actually take all of the periodic or pre-periodic points as a set, then the two sets will coincide only if the two polynomials are the same. So in particular, the shape that I showed you on those earlier slides determines which polynomial I've started with. Those shapes will never be the same if the polynomials aren't the same. And it turns out this is fairly easy to prove using the techniques we learn when we first take a complex analysis course. So it really uses, it's not very difficult to show this, that the shape, in this case, of the set of all of the points determines the polynomial. And so the question that I was thinking about, related to these polynomials, is to take it a little bit further. Well, what if we don't want to take all of the periodic points, all of these periodic configurations? What if we want to just take some of them? How many do we need to determine the polynomial? What's the minimal amount of data that I really need to determine what my dynamical system is? How can we pin it down with the least amount of information? And I'm referring to geometric information here, really the sets of points in the plane. So another way to formulate that, if you take two distinct polynomials and the associated recursions, how many common pre-periodic points can they have if they're not the same? If they're the same, then they have infinitely many common pre-periodic points because they're the same. So what is the overlap of those sets? And it turned out that this question did not seem to have an easy answer just from using complex analysis or the standard methods from dynamical systems that have been well known for a number of years. By the way, I should just make a remark. This type of question could be asked for a much larger class of dynamical systems. It's a very common thing to look at the periodic points or cycles of a flow or of a discrete dynamical system. This is not special to this class, but one of the things I mentioned on the earlier slide, this is one of the simplest examples that one could look at, but yet we still know very little overall about these dynamical systems. And it turns out that the features of this particular family of examples, which seems very simple, maybe naive, maybe very special, turn out to arise in a much broader class of systems, the same types of features that they exhibit related to the structure of those sets or the bifurcations that they undergo. The things that we've learned just from studying this class of examples has told us a lot about much more complicated examples. There are a lot of reasons to focus on this simple case. We thought it would be easy. How many common free periodic points can two distinct examples have if they're not the same? Okay. Oh, I forgot. I have to click here. Let me give you an example so you can see what I'm referring to, or why it might not be obvious from a geometric point of view. So to show you an example, so remember I showed you this picture before. This is the case where C is 0. So in other words, I'm just iterating the squaring function. You input a number, you square it. Then you input the square and you square it again. And then you square it again. And you square it again and you square it again, etc. That is the dynamical operation. And if you're taking some complex analysis or thought about the complex numbers, you know that all of the points that start out inside the disk of radius 1 under squaring will just shrink down to 0 under iteration. And anything outside the unit disk will go off to infinity under iteration. And the points on the circle will remain on the circle of radius 1 forever under the squaring operation. The periodic points, in fact, the pre-periodic points, I should say, are exactly the roots of unity that are dense on the boundary of the circle. Exactly the roots of unity, together with 0. If you start at 0, you stay at 0 under squaring. So 0 and the roots of unity are exactly those points. Now, if I'd like to know what is the overlap of those pre-periodic points with, say, these pre-periodic points, what is this one? This is the example of C equals -1. And if you plot, as I said, all of the pre-periodic points, you'll trace out this very fractal boundary, together with some discrete collection of points on the interior. So you'll pick out this interesting fractal boundary. Now I want to know the overlap, so I might look at the intersection. Here I've just superimposed the two pictures. And it might look, if all the pre-periodic points are here on the circle, it might look like there's in fact very little overlap between those boundaries. So therefore, very few common pre-periodic points. But unfortunately, if you zoom into this picture, this is a zoom, by the way, of this part right here. This is, of course, this fractal curve here is self-similar. So all these bumps and interesting things you're going to see at a repeated scale at every stage. So if this is the circle cutting through, you can see already by zooming in that it seems to hit the boundary in several points. And you zoom in further and it will intersect the boundary even more. And it's not at all clear from these pictures whether or not there's infinite intersection or finite intersection. Now, the periodic points are dense on this curve for this C equals 0 example, and dense on this fractal for the other example. But even if they intersect infinitely often, it doesn't mean those pre-periodic points are common. They might just miss the pre-periodic points. Not at all clear. But what this suggests is that a relatively straightforward complex analysis or topology argument is not necessarily going to help us to understand this intersection. We have to somehow exploit the algebra of these polynomials. Let me show you a few more pictures just so you can see. It gets much worse than this example. Here is the circle again, superimposed with a small perturbation. Actually, a fairly large perturbation. I exaggerated it so you could see the red and blue on top of each other. But if this C were much closer to 0, you really wouldn't be able to see in this picture much of a difference of the shapes. You'll see that those boundary curves, one being a circle and the other being a fractal circle, have a lot of overlap. Another example just to show you. Here is a red and blue shape that almost look the same. Here, let me separate them out. I'm taking one of these, which again, this dark region is where all of the pre-periodic points are for this example, and then another example. Here are the particular examples I've chosen. For these two examples, there's lots of overlap of the sets. This one looks like it contains an entire integral in the real line. This one may or may not contain an entire integral. I can't quite tell what I've plotted there, but it's very difficult to tell just from the shape, or just the geometry, or just the analysis of the picture. And so, the first result, or theorem, that I want to mention, that I wanted to state today, is that we were able to resolve part of this question by observing that even though the sets can have very complicated overlap, or rather the shapes or the closures can have very complicated overlap, the actual set of common free periodic points is always finite. So for any pair C1 and C2 not equal, the two polynomials generating these sets of free periodic points can only have finitely many of those special points, those free periodic points, in common. This, by the way, was some work with Matt Baker from just over 10 years ago, so published in 2011. And it was independently, this result was independently obtained by Xinyi Yuan and Shou Zhang, using similar methods, but a slightly different approach than what we did. We were working at the same time, hadn't realized that each other was working on the same problem. And so we realized, by bringing algebra into the story, by bringing number theory, or indeed arithmetic geometry, into the study of these complex dynamical systems, we were able to get a little bit more information. And so with one example, let me show you, sorry, I forgot this was on the next slide. Notice this does not actually answer this question. All I've done is say the answer is a number. It's not infinite. But it doesn't tell us, this theorem only tells us that there are finitely many, so there is a number, but it doesn't tell us how many. So this is not the end of the story. That's what I want to say. It hasn't actually answered the question. But at least we know the question is a question that makes sense. There is a numerical answer. This is the one example I'd like to illustrate. In this particular example, which is the one I started with, again, I'm looking at the two recursions. One is just the squaring operation, and the other is you square the number and then you subtract 1. And so you get the circle in one case, and you get this, what we call, in complex dynamics, we refer to this particular fractal region as the basilica, because it should look like, if you imagine a lake cutting across the center here, and some beautiful cathedral reflected in the lake. This is what it makes our community think of when we refer to it as the basilica. So the basilica fractal here and the circle. Now, there are three obvious points in the complex plane which are pre-periodic for both. 0 is. So for the squaring operation, I already said 0 squared is 0. It's not moving. There's no motion for this point. But if you put in c equals minus 1, 0 squared minus 1 takes this point and sends it to negative 1, which is over here. But if you do it again, negative 1 squared minus 1 brings you right back to 0. So for the squaring operation, this point is fixed. For the minus 1 case, it goes from 0 over to minus 1 and back again. On the other hand, minus 1 for the squaring operation, squaring minus 1 brings us to 1, which under squaring is fixed. So that's pre-periodic also for squaring. And 1 squared is also, 1 squared is 1. So that's also fixed then for the squaring operation. So these three examples, negative 1, 0, and 1, are 3 points that are pre-periodic or periodic for those two examples. Are there any others? Remember, I showed you earlier that the intersection, so all those other pre-periodic points for the circle are going to lie, they have to lie on the boundary on the circle itself. So the only place where you could have common is at these intersections here, and here, and here, and here. Remember the zoo with the fractal curves. By thinking of the question algebraically, we can observe, I'll just mention, in mathematical language, it turns out this is it. These are the only ones they can have in common. The mathematical explanation is that, it's written here in shorthand, any collection of common pre-periodic points has to be what we call Galois invariant. Remember that these points were solutions to these polynomial equations. The coefficients of those equations were written in terms of c. They're integers. So if you have this list of polynomial equations and you have common roots, well, then all their other roots of those, their corresponding minimal polynomials, are also roots. And we know exactly what the other roots would have to be for the points that are on the circle. If you had a point here, which was a common pre-periodic point, then you would have to see some kind of collection of points spread out all around the circle at various roughly uniform intervals here, which would therefore also have to be pre-periodic. And we can see from the picture, it requires a simple proof, that this entire arc of the circle is not in this set. So it cannot contain any common pre-periodic points. So we can use something about the algebra to deduce, combined with the geometry of the picture, to show that those are the only three. Those are the only three such points. I realized I forgot to check my clock when I started. Do you have any idea what time I should stop? I want to make sure.
You've been talking for approximately 30 minutes.
Is that right? Great. Okay. Thank you. All right. So this is the kind of argument that we use to prove the general theorem. The theorem was up here. For any pair of points, these polynomials have only finitely many common pre-periodic points. Now, I should take a moment here. I've actually sketched the entire proof on the next slide, but that is really and truly for the mathematicians in the audience. The only sticking point is that I've stated a theorem here, I didn't write it, but for any complex numbers, C1 and C2. And the argument that I described doesn't really make sense completely for complex numbers, if I've described it for integers. Because this issue about all those roots of the polynomial, and minimal polynomial, and Galois invariants, and one has to be careful. So just so you at least see it, this long slide is a sketch of the full proof of that theorem, modulo some technical details. So I just want to mention what some of the key ideas are. We're really using algebra and number theory to prove a result about complex dynamics. And what we do, so just so you can see it, is the first step. Let's just begin by treating the case where the two parameters here, C1 and C2, are algebraic numbers. So that means they themselves are roots of some polynomial equations with integer coefficients. Then we work at a particular field extension of Q, where we adjoin those 2 points. This is some number field, if you're familiar with this language. And we study then the set of common pre-periodic points, and that statement about all the corresponding roots of the polynomials are also common pre-periodic points is a statement about this Galois invariance, which still holds. But then there's a geometric component. What do all of those Galois conjugates look like? The statement, in fact, the theorem, or one of the theorems is that if that set is infinite, if there are lots of common pre-periodic points, then geometrically they must be uniformly distributed on both of those filled Julia sets, on those boundaries. So you have two different dynamical systems, two different shapes. We know those define two different fractal shapes, but we have this set of points which is uniformly distributed on both of them. And we already saw that if the shapes are the same, then the polynomials have to be the same. And this argument makes sense in the algebraic setting, and then just a quick remark, if they're not algebraic, and let me just make some comments, if they're not algebraic, and this was really the main point of what we were doing, how do you use algebraic techniques to get to something which doesn't seem algebraic a priori? And so what we actually do, and I just have to say the words, because this is what we're really doing, is we're doing a geometric argument, what we call an equidistribution argument, that takes place not in the complex plane, not on that corresponding filled Julia set, but in some non-Archimedean analytic space called the Berkovich analytic space. But we essentially run the same argument at the end of the day. We just don't work on the complex plane. So I cannot show you a picture, I'm afraid. There are no good pictures of this space. This is a sketch of how the proof goes. Well, let me move on. So returning again. So this was the statement that I mentioned. So again, for these particular recursions, for any pair of them, you can only have finitely many common pre-periodic points if they're not the same. And as I said, this did not actually answer this question, how many common pre-periodic points can you actually have? And this now is the starting point of the work that I was doing with Krieger and Hexi, and which began at AIM, where we proved a uniform bound on that number of common pre-periodic points over any pair of such polynomials. Okay, the theorem says there is a uniform bound. There's some number, m, so that any distinct pair of polynomials over the entire family, any distinct pair, can have at most m common pre-periodic points. There is some number, m. You can't have any more than that. So it means there really, truly is some answer to this question. There is some number. You never have to look beyond that. You need only that many points in the plane. And if you know that they're pre-periodic, that will pin down uniquely your dynamical system in this particular family. And the argument to do this was to take a lot of those same ideas, that idea of using the algebra together with the geometry and the analysis, but to soup it up a little bit and get a quantitative version. It had to do with, we know the points become spread around and uniformly distributed in our space. How fast do they become uniformly distributed? How many do you need before you know your points are very close to the entire shape or the limiting distribution? So it's a quantitative version. And so this was the starting point, and what led, this is the work that really led to the development of the article that brought me here today. This was ingredient number 1, or step number 1. I should say, by the way, and I have this on my slide, mathematicians ask me all the time, so what is m? Right? What is this mysterious number? I suspect that this number is no bigger than 100. I'll show you some examples later. It shouldn't be any bigger than 100. And in fact, what's interesting is that our methods give us a number. It actually spits out, if you run through the entire procedure, it spits out an explicit number. But unfortunately, the number is huge. The proof gives a terrible bound. This is so completely impractical. You could never test 10 to the 82 points. And this is an absurd number. We were delighted that we could get an actual number, because in mathematics this is often very difficult to run some machinery. You have an existence argument. You know that number exists, but what is it? Can you make your proof work to give you an actual value? Yeah, and it did, but that's what was a little disappointing. So I would be delighted to know more about how big this really can be. We don't have examples that go up beyond 20-something right now. So I'll show you some examples at the end. All right, so now, all of this that I've been talking about for more than 30 minutes, for quite some time, was all supposed to illustrate, again, this idea of working and wanting to understand a class of dynamical systems that have been traditionally studied from a complex analytic or even topological point of view, and to introduce and to bring in some ideas from number theory and the algebra, and try to use it to get answers not just about the algebraic case, not when C1 and C2 are integers or rational numbers, or not just in that case, but in general, also for complex numbers. And so that was really what we were going for, and which is how this is really for all complex pairs, I should emphasize, all complex number pairs, where the machinery is a little bit different. So all of this was bringing some arithmetic into dynamics. But if you recall from the slide that I showed at the beginning of the talk, that was all this arrow right here. Okay. So all of this was to illustrate an example of using arithmetic geometry in the study of the dynamics. In this case, it was polynomials. If you just add a point at infinity, you can think of the complex plane as a sphere. But that was a special example, a special class of examples of dynamics on the sphere, in other words, on a Riemann surface of genus 0. Okay, so now, in a few minutes, I'm I'd like to tell you everything else, which is about the content of the other paper, this paper with Polly and Hexi that I wanted to talk about. Okay, so I feel obliged to state the theorem accurately, although it's technical. I would like obliged. I feel it because I feel it's important. I'm not actually obliged. I would like you to see it. I would like you to see the actual statement, and I will say a few words about it, and then I suppose you can forget the actual statement. But just to tell you, this was the main result of the paper. So let me read through it and then try to explain what some of these objects are. We were studying a particular family of surfaces, what are called compact Riemann surfaces, in genus 2. This is a picture. This is a drawing of an example surface in genus 2. The genus just refers to how many of these donut holes you see in the shape. But not just any old surface of genus 2. We were specifically looking at ones that have a little bit of extra, have some symmetry. In other words, they admit, in this case, that have a degree 2 map down to a genus 1 curve, what we might call an elliptic curve, because there's some distinguished points here. So this Riemann surface admits a degree 2 map to elliptic curve. That is not all genus 2 curves. That is what we call a codimension 1 condition in the space of all such. So let me just mark, I've written it here. This corresponds to a 2-dimensional, a 2-complex dimensional, or 4 real dimensional family of such surfaces. Okay, so these are the objects we were looking at, this particular collection of Riemann surfaces. Now for each one of those, it sits very naturally inside of a certain 2-complex dimensional torus, what is called its Jacobian, which I will not define, but there is this natural object, this object which is attached to the information of this Riemann surface, and this surface, this real 2-dimensional surface, this is now real 4 dimensions, this thing is sitting very naturally inside this space. This kind of comes for free with the data of the object we started with. Now, all of this object here is it happens to be a group. It has a group structure. This red dot represents the 0 of the group, and all of these other dots, the polka dots, correspond to what are called torsion points. There is a dense collection of torsion points inside this. It's a complex torus. Inside this 2-dimensional complex torus. The torsion points are just the points that have finite order in the corresponding group structure. All right, so these curves are sitting naturally inside. We're actually looking at a particular way of putting them inside. All of these surfaces here have, in addition to the symmetry I'm requiring regarding the donut holes over the genus 1 curve, there's an additional skewering symmetry here that it has. And I'm just requiring that one of those 6 skewer points goes to the red point. Okay, that's a technical condition, but I wanted to state the theorem accurately. So I'm looking, again, at this family of genus 2 Riemann surfaces sitting inside the Jacobians, where one of these special hyperelliptic, the fixed points of the hyperelliptic involution are sent to the 0 of the Jacobian. Theorem, there is a uniform bound, uniform by which I mean independent of which surface you're looking at, for which the number of intersection points of our Riemann surface with these polka dots is bounded by m. There are no more than m, there's some number m, for which there's no more than those number of torsion points on this Riemann surface of genus 2. That's the theorem. All right, who cares? Why is this important? Why is this interesting? Why are we interested in this? So there's a long history, and I've mentioned only a couple of the names that go into this study, but let me just say, the fact that anytime you take one of these things and you stick it in its Jacobian, it was known that it would only hit finitely many of these torsion points. That finiteness was a conjecture, it was a question. It's referred to as the Manin-Mumford Conjecture. It was proved in the 1980s that intersection is always finite. This has some geometric geometric significance for our understanding of these surfaces. Okay? So that was proven in the 80s, and in fact, shortly after that, Barry Mazur, who works in number theory, should have said, actually, there's no obvious number theory in this, and I'm saying dynamics and arithmetic, so I'll come back to that. But in any case, Barry Mazur asked, well, how many points does it intersect? And can you control that number of points just in terms of here, the genus, in this case, in terms of the number 2. The genus is 2 in this case. So he asked if we could control this number of intersection points. Now, there has been work on this question since 1986, certainly, and in fact, essentially all of the work was from an arithmetic or a number theoretic perspective. There are a lot more tools you can use if this Riemann surface is defined by some algebraic equations that are, say, defined over the rational numbers. So if this thing is defined over the rational numbers or over a number field, there are extra tools that we can use to study how this object is sitting inside its Jacobian. And all of the bounds that were known involve what's called the field of definition of these surfaces. So a uniform bound is not known for any family, as far as I'm aware, except at least in a field-independent way. So all of the existing bounds depended on what we call the field of definition. But here, I'm working over the complex numbers. This is not an arithmetic statement, and this is not an arithmetic type of question, and we were looking at a family of complex surfaces. And so we wanted to eliminate a field dependence. I have to mention some very exciting developments in this direction from just this year. So, which now supersedes what we've done, and it's a really, really beautiful piece of work. So just this year, Lars Kuhne completed a proof of the existence of a uniform bound, answering Barry Mazur's question, depending only on the genus. It works in every genus, and it works for all of the Riemann surfaces over the complex numbers. So he gives a proof of the full uniformity conjecture. In other words, for any Riemann surface of a given genus, you embed it in its Jacobian, not even by a hyperelliptic embedding, by any, it doesn't have to even be hyperelliptic, by any embedding, and there is some uniform bound that depends on the genus. So a really lovely piece of work. And his techniques, I should mention, here, I just want you to observe these words right here, include some equidistribution, which is a word that I've already used when sketching the proof of the previous theorem. Use some techniques, this arithmetic equidistribution techniques. So he's also using arithmetic tools and height bounds. I just want to mention that for the mathematicians, which is also an ingredient of our proof. And so there is a lot of overlap in spirit, but it's a much more powerful result that he has obtained for his equidistribution and for the height bound. So it's really fantastic. So this is really an exciting development. Because not only, by the way, so for the mathematicians, I should mention, not only do they get uniformity for this Manin-Mumford problem, but they also get he, building on this earlier work, also gets uniformity in the context of Faltings Theorem, the Mordell Conjecture, and so I won't say any more than that, but for those of you who know what the problem is, you're probably also aware of this work, but I just want to advertise for this really fantastic recent developments on these problems and the type of mathematics that goes into solving them as well. All right, so this was the work that we were doing. So this is the paper that we wrote, the uniform Manin-Mumford for this particular family of genus 2 curves. Okay, so this is what was special there. It was so that just to emphasize that what we were excited about was this was being the first time that we could get a bound that does not depend on the field over which this object was defined. We worked over the complex numbers. Okay? But it was still an algebraic proof. And so I wanted to say just a couple more words. I have actually something like 20 more slides, but I won't go through all of them. I wanted to illustrate a few more ideas that go into the proof, maybe by pictures. Let's see if I should. There's one concept that I want to introduce. Yeah, there's one important concept that I want to introduce before I finish up. I talked about iterating certain polynomial functions at the beginning of my lecture. Degree 2 polynomials, z squared plus a constant, and the iteration of those. But one can iterate much more complicated functions. They don't have to be degree 2, they don't have to be polynomials. And in the class of all of such objects that we're interested in studying, there's a very special class of rational functions that one might iterate that come from the arithmetic, the geometry of elliptic curves. And so, just to briefly mention, an elliptic curve has a group structure. I've already mentioned this word earlier. The notion of a torsion point is one which has, under some, when you add, there's a notion of addition on this surface up here. You can add points to each other or to themselves, and a point is torsion if when you add to itself enough times, you come back to the zero. There's a 0 point, and then you can add. So there's arithmetic here. A point, remember, is pre-periodic for a dynamical system. One can define a dynamical system up here, which is just adding a point to itself. So the dynamical system is you start with a point, you add it to itself, and you call that 2 times p, because it's just p plus p. So this induces a dynamical system. And it turns out that dynamical system, well, it plays well with the group structure because it's defined in terms of addition. So the pre-periodic points for this dynamical system are exactly the torsion points. And it turns out that this defines a dynamical system, which turns out to be a rational function, in which the pre-periodic points are exactly the projection of those torsion points. Sorry, let me be very explicit. I realize my next slide is everything can be done by hand with formulas, and so maybe this is rather abstract. But the point is, one can look at this particular collection of rational functions. Now I'm not writing z as my variable, but x is my variable. So if this is the function which defines your recursion, that is, you start with a point x, you apply this particular rational function of x, and that's your output, and then you plug it back in. So it looks messy when you start writing out the values, but it is something that can be iterated. Okay, so this is going to define the recursion, and this is a formula for those that actually come from a family of elliptic curves. So this is an explicit computation of these recursions that you get from the group structure on an elliptic curve. Okay, so it's a special class of recursions. All right, who cares? Why do we want to know this? Because in the study of geometry of elliptic curves, there was this question in the literature, in the recent literature, there was a question in the literature about, in order to study the geometry of these objects, which have been studied for many, many, many years, the question was, well, what happens if we, instead of looking up here, we look down here and do this iteration down here on the Riemann sphere, on the sphere here? And the question, or the conjecture was, there's a uniform bound, say m, so that these are called lattice knots. There's a uniform m, so that if you take any pair of these for distinct parameters, I'm now calling them t instead of c, so that for any distinct pair of examples, there would be at most m common pre-periodic points. This had some implications on the geometry of elliptic curves related to how many points in common, or how many points really determine this elliptic curve. So this conjecture was there in the literature, and this should remind you of the theorem that I had stated earlier. It's just that now it's for a family of rational functions instead of those polynomials. So let me skip ahead to let me skip a little bit of the history. Hold on, I'll go back to that in a second. Sorry, I just want to remind you. So this is the theorem I had stated earlier. There is a uniform bound, so that any pair of degree 2 polynomials have at most m common pre-periodic points, as long as they're distinct. And the question was, is the same thing true for this particular, instead of these recursions, how about these recursions? Okay, so this particular family of recursions. But this was related to studying elliptic curves. And before I tell you the answer, I wanted to go back just a moment. This was my title slide. This picture on my title slide is an illustration for one of these examples of what those pre-periodic points look like. So unlike in those polynomial examples where you saw those nice fractal curves that fit into some box in the plane, this picture, these white dots, if you fill them in, are going to fill in the entire plane. They're actually dense in the entire sphere. The pre-periodic points for these examples are everywhere. So the geometry of that set, you take its closure, you get everything. They're going to be the same no matter which one you look at. So we can't use sort of naive topological or geometric arguments to address these sets. I've only plotted some of them, as you can see. Otherwise, my picture would be entirely white. I only plotted some of them. But that's what this picture is. I just wanted to mention. And so, just to then go back and to finish, so this was the end of the story. This was the question. This is what we proved for polynomials. We realized that some of the techniques carry over, not all of them, but some of the techniques carry over. The same philosophy of equidistribution, using the algebra, working on a Berkovich space, all the words that I mentioned earlier can be used to study this family of examples. And lo and behold, this statement turns out to be equivalent to the theorem that I mentioned earlier. It looks totally different. It's about elliptic curves, families of elliptic curves, families of recursions. For that very particular class of functions, it turns out to give this statement about this two complex dimensional family of Riemann surfaces in genus 2. And then there is an explanation for how they're related, but I think I might need to skip it because I think I've gone over the time that I thought I would have, so I'm just speaking more slowly than I.
No worries.
I just wanted to say just one thing to explain this picture. Especially for the mathematicians in the room, just to say oops, oh my gosh, look what I just did. I pressed the wrong button. There we go. Got it back. That's the sign that I should stop. Just to illustrate what this picture has to do with this picture, if you take two examples and you work on a two-dimensional space, this surface, the product of these two things, you take two different maps here, coming from, say, two different elliptic curves, it turns out that each of these surfaces, so I said I'm assuming there exists a map to one elliptic curve. For free, it turns out you automatically get a map to another elliptic curve. This product of elliptic curves here turns out to be closely related to that Jacobian. It's not exactly equal to that Jacobian, but that complex torus that I mentioned earlier. So there is a connection between these genus 2 curves and the genus 1 curves and the genus 0 curves. But it turns out these statements are actually logically equivalent. Perhaps not for the same m. Maybe this m needs to be 4 times this m. But since our computations show that m is something like 10 to the 100, that's irrelevant. Because 4 times 10 to the 100 is just as bad. So this is the last part. Let me skip ahead a second. The last thing I wanted to say was how big can these sets be? I just wanted to show you a couple pictures to finish. I mentioned that returning to the case of polynomials, the current record holder, in the sense of finding 2 examples that have the most common pre-periodic points that we could possibly find, occurs for this particular pair of polynomials. Those of you from my workshop who are studying arithmetic dynamics might have seen these very particular examples before. Notice these are rational values of C. They appeared in some other contexts that I will talk to those people about later. But the beauty of it is the number of common pre-periodic points for this example is at least 27. This is the record holder right now. Remember, our bound was 10 to the power 82, which is absurd. This is the largest we've found so far. We don't know, what the largest actually is. This is a plot of the 2 different pictures on top of each other. And here they are individually, so you can see what they look like. But you don't get a whole lot of information from those pictures. This is a list of what the actual numbers are that we found. There might be more, we don't know for this particular example. We don't know what's special about these two examples. We don't know a whole lot. And so I think it's a really fun challenge to try to figure out what is special about these examples. Is there anything special about these examples? Are these even the record holders? Maybe there are other pairs that give us more. Can we even compute more examples? We don't have a whole lot of data on this, and so computationally it would also be interesting to run some experiments to try to see how big we can get. So with that, I finish. Sorry.